This lesson concerns hyperbolas. Before studying this lesson, you should already know about ellipses and be familiar with the equation of an ellipse when it's in standard form, how to find the vertices, and the length of the major and minor axes. You're going to find in this lesson that as far as the equation is concerned, it looks very similar to the equation of an ellipse. And there will be some other similarities about things that we used from the equation to locate vertices. But the graph of a hyperbola looks considerably different. Let's start this lesson by looking at the definition of a hyperbola. A hyperbola is the set of all points in a plane for which the difference of the distances from two fixed points called foci is a constant. Now you'll notice this definition is very similar to the definition of an ellipse. We have a set of all points, but notice here, instead of finding the sum of the distances from two fixed points, we're taking the difference, we're subtracting those distances. This time when we subtract the distances, we get a constant. You'll notice these two fixed points are still called foci. Now I want us to look at the equation of a hyperbola next. The graph of the equation x squared over a squared subtract minus y squared over b squared equals 1, or y squared over a squared minus x squared over b squared equals 1, with a greater than 0 and b greater than 0, is a hyperbola with center at the origin. Let's stop there. Notice these equations look almost like the ellipses. What's different? We're subtracting here, aren't we, instead of adding. Another difference that I want you to notice, here x squared is over a squared. Here y squared is over a squared. Here we're going to identify a not in terms of which one is larger. You'll notice over here it doesn't say anything about a being larger than b. That doesn't matter. All we are saying here is that both are positive. Here we identify a by which number is under the term that is in front with a plus sign, if you will, understood to be there. Notice the term that is being subtracted always has b under it. Sometimes we're subtracting the y squared, sometimes we're subtracting the x squared. So a will be the number under the positive term in the equation of our hyperbola. Now let's notice we have what's called a transverse axis. We'll have a length of twice a conjugate axis of length twice b. Recall with an ellipse we did do something about twice a and twice b. We call that a major and minor axis. Here we use different words. We have a transverse axis of length 2a and a conjugate axis of length 2b. The foci are on the line containing the transverse axis. The transverse axis will have that involving a in it. Now, what's the difference in the graphs? With ellipses, it depended on whether a was under x or y in terms of whether the ellipse was elongated vertically or horizontally. Let's look at a graph, and I'm going to talk about the difference between these two equations. The first graph that I have for you looks like this. Now, this is your y-axis and your x-axis. These dark lines here are actually the graph of a hyperbola. You'll notice that a hyperbola looks sort of like two parabolas going in opposite directions, if you will. It is not an ellipse. Notice the ellipse, remember, was sort of circular in nature. Now, this box that we have here is referred to as the central box, and we'll be talking about how we find that box. These dotted lines that you can sort of see, I didn't want them very dark here. These lines coming across here are asymptotes for our graph. You may or may not be familiar with asymptotes at this point. Basically, asymptotes in this case are guidelines for us. Our graph is going to come out and get very close to these asymptote lines, but it will not cross or touch the asymptote lines. So these asymptotes are a guideline to help us know how fat, if you will, these hyperbola branches are. We talk about this as being two branches of our hyperbola. Now, as far as the equation is concerned, this hyperbola would have come from an equation like this first one, where our x squared term, x squared over a squared, is our positive term. So if our positive term is the x squared, our hyperbola is going to open on the x-axis like this, from side to side, horizontally like the x-axis. Now, this transverse axis that we're talking about here of length 2a, the transverse axis is actually from this point on our hyperbola to this point over here. So twice a is this distance across here. So that says a gives me the distance from the center 0, 0 out to this point here. These points that I'm pointing to here will be the vertices of our hyperbola. We'll be looking at that in a second. Now, this distance across my box across this way is called that conjugate axis. Notice our conjugate axis had a length of twice b coming from our equation here. So from 0 up to this part of our box is b, from here down is negative b, so the total distance across here is 2b. So from the center out to here is a, from the center up to here is b. We use a and b then to help us draw this central box that we're talking about. And then to get our asymptotes, all we have to do is connect the opposite corners of this central box. That gives us our asymptote lines. And then from our vertex points, we will sketch in our hyperbola graph. We'll know which way to sketch it, because remember, if the x squared over a squared is our positive term, then our graph will be horizontal like the x-axis. Now, I have another graph here, which you'll notice is another hyperbola, but this one is opening up and down vertically like the y-axis. That would come from this second type of equation where the y squared over a squared is our positive term. So if our y squared is our positive term in front here without the negative in front of it, then we open vertically. The distance from 0 to this point would be our a. This would be our transverse axis. Our conjugate axis would be across here. It would have a length of 2b. Again, we would use the a and the b to draw this central box, connect opposite corners to get our asymptotes, and then from our vertex points we'll know how fat to draw in our hyperbola. You'll become more familiar with that as we do examples. Our equations will look like this. Twice a is the length of our transverse axis, twice b the length of our conjugate axis, and basically we use those axes to get our central box. Now, I've been talking about the vertices. Let's look at that. The distance from the center to a vertex of a hyperbola is a, okay? And remember, we'll do a horizontally if our x squared over a squared is our positive term, and we'll do a vertically if our y squared over a squared is our positive term. The distance from the center to the focus of a hyperbola is c. C is given by the equation c squared equals a squared plus b squared. Now remember, with the ellipse it was c squared equals a squared minus b squared. And I referred in that videotape to, it helps me to remember the Pythagorean theorem. The way I remember when do I subtract and when do I add, for the hyperbola my equation has a minus sign, and notice to find c I do addition. On the ellipse, my original equation has a plus sign. Remember, x squared over a squared plus y squared over b squared. And I subtract to find c. So that just sort of helps me remember these. Now, let's take this information to an equation and see if we can't sketch the graph of a hyperbola. We're to find the vertices, sketch the central box and the asymptotes, and then the graph of our hyperbola. Let's look at this equation. X squared over 9 minus y squared over 4 equals 1. Notice I have x squared over a number, subtract y squared over a number equals 1. Looks very much like the equation of the ellipse, but we're subtracting. Since our x term, our x squared over 9 is our positive term, 9 is our a squared. So a squared equals 9 gives me a equals 3. Okay? My b squared is 4. That's under y, so my b is 2. Okay? Now, let's pick a point over here to be our origin. And just to be sure that you can see these lines, let me do a quick little XY axis for us over here. Okay, since our x squared term is our positive term, then we know our hyperbolas are going to be sideways, horizontally like our x-axis. So from the center of 0, 0, we're going to go a distance of 3, 1, 2, 3 this way, and 3 this way. We're going to use B to go up 2 and down 2. Now, so far, that's been just like what I did with an ellipse. But this time, instead of sketching in an ellipse, what I'm going to do here is sort of dot in my central box. You'll notice I'm making a box using these points that I've sketched here using A and B. There's my central box. Now, I wanted my box so that I could connect these opposite corners. Now, you'll notice what I'm doing here is simply dotting in both the central box and where these asymptotes are. I don't want to make solid lines because these are not actually the graph of the hyperbola. They're simply guidelines to help me get that graph exactly correct. Okay, so I'm going to dot in my 2 asymptotes and my central box. Now, again, since my A is under X here, and X is my positive term, then these are my vertex points using my A horizontally. And so from my vertex point, I will come out and notice how I'm approaching these dotted lines. The dotted lines sort of tell me how fat my hyperbola will be when I sketch it in here. Now, my vertices are on the x-axis, so my vertices are at the point plus 3, 0 and minus 3, 0. I'm going to write that together, plus or minus 3, 0. Now, I have found the vertices, I've sketched my central box and asymptotes, and I have sketched in my graph. Now, your instructor may want you to find the foci. Remember here, c squared equals a squared plus b squared. If I have minus in my equation, I add here. So c squared is my a squared of 9 plus my b squared of 4. 9 plus 4 is 13. So c is the square root of 13. Now I'm going to go to my calculator to approximate the square root of 13. And I'm getting about 3.6. Now I want to show you that my foci will be on this line containing my transverse axis across here from the origin. If I go 3.6 and negative 3.6, notice that my foci will be inside where my hyperbola sort of curls around it. That will always happen. My foci will be inside here. So the distance c, notice, is going to be more than a, because to find c I'm adding a squared and b squared. So my foci will be inside there. The coordinates of my foci then for this hyperbola are plus or minus the square root of 13, comma 0. That would be the location of my foci. Now, if you wanted to, you could also find the equation of your asymptotes. Some of your instructors may require that you do that. Notice that my asymptotes, I have 2 of them, are going through the origin 0, 0. Okay? Remember the form y equals mx plus b? This is the slope y-intercept form. Well, since both of these equations go through the origin, my y-intercept is 0. So basically, both of my asymptotes have an equation that's just y equals mx. And remember, to get slope, slope is a change in y over a change in x. Well, let's look from the origin to get on this other point on this line. I'm going to go up 2 and this way 3. That's my a and my b numbers, isn't it? Up 2 and to the right 3. So for this asymptote, my slope is y changes 2, x changes 3, y equals 2/3 x. Notice for my other asymptote, to get from this origin down to this point, I will go down 2 and to the right 3. That gives me a negative slope, negative 2/3 x. So you can actually just write the equation of the asymptotes by looking at the fact that it goes through the origin, giving you a y-intercept of 0, and then change in y over change in x using your box here. And notice for the other asymptote, your change in y is negative. So those are not really difficult. Again, your instructor may or may not require those equations, but that's how you'll find them if they do. Let's look at this equation. We have y squared over 6 minus x squared over 15 is equal to 1. Notice this time my y squared over 6 is my positive term. I'm subtracting the x squared over 15, and I have my 1 over here. So my a squared this time is the number under y. Notice it has nothing to do with which one is bigger. 15 is actually bigger. But I have to identify A for a hyperbola as the one underneath my positive term here. So A is the square root of 6. I'm going to go ahead and go to my calculator and approximate the square root of 6. That's about 2.4. And then my B squared will be 15. So B is going to be the square root of 15. And again, I'm going to approximate the square root of 15 with my calculator. That's about 3.9 if I round off. Okay? Now, let me get, again, an XY axis sketched in for us over here. This time, since my y squared over a squared is my positive term, I know that my hyperbola is going to be vertical like the y-axis. So my a is a distance on the y-axis. So from 0, I'm going to go up about 2.4 and down about 2.4. And then on the x-axis, notice I'm using the number under x. To do this, I'm going to go about 3.9, 1, 2, 3, almost 4, 1, 2, 3, negative 3.9. Remember, again, I use these points to sketch in my central box. Now, you might want to use a ruler to be more accurate than what I'm doing here. There's my central box. And then we will connect the opposite corners of our central box so that we'll have our asymptotes. Again, I'm dotting in both the central box and the asymptotes. As a reminder, that's not part of the graph of the hyperbola, but simply a guideline to help me get the graph. Now, this time, since my y squared term was my positive term, and I know that this hyperbola is opening vertically, up and down, I know that my vertex is this point here, 0, about 2.4. So notice this time my hyperbola is going to be rather fat because I'm going to have to come out to these asymptotes. See how fat that thing is? Without those asymptotes, I would have a difficult time finding enough points to know exactly how that graph should look. Our vertices this time are on the y-axis, so the coordinates of my vertices, x-coordinate is 0, my y-coordinate is plus or minus the square root of 6. Remember, we always list the exact value there. Now, if I wanted to write the equation of my asymptotes this time, notice again we go through the origin, so I just need y equals mx. And since my slope is the same basically, except one is positive and one is negative, I'm just going to do it this way. Notice from here I go up this distance, which is what? That's my a value. And then I go this distance, which is my b value. Well, my a was the square root of 6. My b was the square root of 15. And so my equation would start out looking like this, plus or minus the square root of 6 over the square root of 15 times x. Now you might want to do some work on that square root of 6 over 15. You could, for instance, put 1 square root 6 over 15, and then you can reduce that. If you divide by 3, you get 2 fifths. And then, of course, you could split it back up, square root 2 over square root 5, and rationalize that. If you multiply by the square root of 5 on top and bottom, you get the square root of 10 over 5. So probably you would want to write this as plus or minus the square root of 10 over 5 times x. Notice that all I did was take the change in y. Notice the change in y is given by the square root of the number under y. And the change in x is given by the square root of the number under x. Okay? Well, again, so far our equations have already been in that standard form. Let's look at this one. Find the vertices, sketch the central box, the asymptotes, and the graph. We'll look at your equation. 2x squared minus y squared equals 2. Now, how do I know that this should be a hyperbola? Well, let's look. I have x squared and y squared, but you'll notice this time we're subtracting them. That subtract sign between my x squared and y squared is what tips me off that this is probably a hyperbola. Now, if I recognize I have a hyperbola, remember I want x squared over a number minus y squared over a number equals 1, or those might be in a reverse order. Since I want a 1 over here, I'm going to divide everything by 2. Okay? So I get, notice, x squared, I'm going to write that x squared over 1 minus y squared over 2 equals my 1. My positive term here is x squared over 1. So a squared is 1, giving me a equals 1. My b squared is 2, so b is the square root of 2, which I know is about 1.4. So let's use that to sketch in our hyperbola this time. Since we have our positive term is the x squared over a squared term this time, I know that my hyperbola will open sideways horizontally like the x-axis. So from 0, I'll go over 1. I think I'm going to change my scale here a little bit and use 2 boxes for 1. And then b is going to be about 1.4. So I'll go about 1.4 up and down, and we will use that, remember, to sketch in our central box. Okay, then we will connect our opposite corners. Notice that when we're doing that central box, on the x-axis, we always use the square root of the number under x squared. And for the vertical distance, we always use the square root of the number under y squared. Now, the main thing then is to know which one of those is the vertex point. Well, if the x squared term is the positive term, then our vertex is on the x-axis. So from our vertex points, and notice again we have a fairly fat hyperbola here that we're sketching in. So my vertices this time are on the x-axis, so the coordinates are plus or minus 1, 0. Now I've not really been mentioning it in these examples, but this center of our central box is always called the center of the ellipse, and again it's always at 0, 0 in this particular lesson. But just like with the ellipses, if we learn these basic concepts here, then we can always easily change and translate to a new location and do the same sorts of things that we're doing here. Let's look at this equation. X squared minus y squared plus 9 equals 0. Notice I have x squared and y squared, and there's a minus sign between them. That's what tips me off to look for a hyperbola. Now, you'll notice this time I've got everything on this side of the equation, so let's move that 9 to the other side. X squared minus y squared. Notice that will equal a negative 9. Now, what do I want to get over here? I want to get a 1, and it needs to be a positive 1, doesn't it? Well, to get a positive 1, I need to divide by negative 9. So let's divide all parts of this equation by negative 9. Notice a positive divided by a negative, that's going to be minus x squared over 9. And here, minus, and I have a y squared over a negative, that's going to be a plus. So I'm going to put that one in front. Y squared over 9 equals positive 1. Notice, in this form, it looks like probably x squared would be the positive term, but after I divided, it's got a minus in front of it. So you can't always tell here whether your hyperbola is going to be a vertical one or a horizontal one. Not until you get into this basic form here. Now, my a squared is 9 because that's what's under my positive term here, so a is 3. You'll notice this time b squared is also 9, so b is also 3. All that's going to do is to make our central box a square, isn't it? Because we're going to be going the same distance on both the x and the y axis. Now, you also need to keep in mind then, be thinking about which one of those places would my vertex point be. So on the x-axis, I'm going to go 3 over right and left. On the y-axis, I'm going to go up 3 and down 3. That will complete my box, my central box. So I'll dot that in. And then we'll connect those opposite corners. We're going to have a nice squared up hyperbola here. Now, which one of these places was my vertex? Since my y squared is my positive term, my vertices are on the y-axis. So my vertex points would be on the y-axis here and here, and my hyperbola will be a vertical opening hyperbola like this. So my vertices will be at the point x coordinate 0, y plus or minus 3. Okay? let's go ahead and write the equation of the asymptotes this time. Notice that I will go from the origin up 3, and I will also go to the right 3. So my slope is 3 over 3, which is 1. Notice this way to be down 3 into the right 3. So my slope is either a plus or a minus 1. So my equation of my asymptotes will be y equals plus or minus 1x. Y equals plus x and y equals minus x. Okay, I have one other example for you here. Notice again I have x squared, y squared. They're being subtracted. And so I'm expecting a hyperbola. Notice I already have a 1 over here. Oh, we saw one of those on our tape for ellipses. Since I already have a 1, I don't need to be dividing. So what I'm going to do is simply make those look like fractions by putting them over 1. But can I have this 9 and this 4 here? Recall in the equation of our hyperbolas, it was just like with those ellipses. It's simply x squared and y squared in the numerator. There's no coefficients in front of that x squared or y squared. So what did we do in that situation? Look at this first fraction. If I don't want that 9 here, I can divide the numerator and denominator both by 9. So dividing by 9, I get y squared over 1/9. And then in this second fraction, I don't want the 4, so I'll divide numerator and denominator both by 4, giving me x squared over 1/4 equals 1. So it just turns out that my a squared and b squared are fractions. A squared will be under the y squared since that's my positive term. So a squared is 1/9, making a 1/3. And b squared is 1/4, making, making a 1/3. I didn't need to put an equal sign there. Making b 1/2. Okay? So let's get us an xy axis. And I think I may want to adjust the scale this time since we have those fractions there. I think what I'm going to do, because of this 1/3, let 3 marks be 1. So there's 1, there's 1, and there's 1. So A, notice, is under y. So I want to go 1/3 up. That would be right here. And 1/3 down. That will be my vertex points. Let's go ahead and just write down that our vertices are going to be at 0 plus or minus 1/3. Now, remember I used this b distance on the x-axis, so 1/2 would be halfway between my 0 and 1. And we will use that then to complete our little central blocks. It's going to be a very small little central box this time. And then we will connect our opposite corners. Same thing this direction. And since our vertices are on the y-axis from our vertex points, we're going to come out to these asymptotes. And we have the sketch of this last hyperbola. So what we've seen, the equation looks very much like an ellipse, except instead of adding those, we're subtracting. And we identify A by which term is positive. A may be under x or it may be under y. If our A is under x, if our x squared over a squared is our positive term, our hyperbola will open to the side like the x-axis horizontally, and our vertices will be on the x-axis. If we have our y squared over a squared as our positive term, then our hyperbola will open up and down vertically like the y-axis, and our vertices will be on the y-axis. Again, if you're asked to find the foci, this time you use the equation c squared equals a squared plus b squared to find the value of c. And the distance from the center 0, 0 to the focus is that distance c. Those foci will always be sort of inside those two parts of your hyperbola. Your hyperbola curls around those foci points. You have your transverse axis of length 2a, your conjugate axis of length 2b. And actually that transverse and conjugate axis is what you use to sketch in that central box. Connecting opposite corners of your central box gives you your asymptotes. So then from your vertices, you will approach those asymptotes with your graph. If you're asked to find the equation of your asymptotes, recall that your asymptotes go through the origin, so the y-intercept is 0. And you can calculate your slope. Use y equals just plain old mx since your b is a 0. I hope that this has helped you with hyperbolas. And perhaps with this background, then you'll be ready to do the more general hyperbolas that are not centered at the origin.